brief video is the first step in accomplishing assignment 1B, a set of calibration curves. And we're going to start first with clicking on the calibration linear XLS. So not the number 2, just the one above it. These aren't in sequence, but anyway, they're in alphabetical order. We'll do the linear first. So we click on that, and it'll download. You see it downloaded over here. Now we click on that to open it. We'll have to enable it. It has a lot of formula in it and everything, and it came from the internet, but it's good, it's safe. And the first thing we want to do is get oriented. And we see the instructions over here on the left. We're going to put in our concentration of our standards here. It has several slots from B6 to B25. And then we'll have to put in some instrument readings. And what we're going to do, just to get it going, is to put in some numbers, and then it says to delete a value, click on the cell and press the space bar. So we'll do that for the remaining ones because it's going to automatically graph our instrument readings against the concentration that we put in for our standards, and then it'll be calculating the residuals. The residuals, if we let's see somewhere here. This standard deviation of the residuals here is referring us to sheet 2. So when we click on sheet 2 down here, we see this is where these calculations are going to be made for filling in some of the formula over on this page here. Now it could have been over here on the right or anywhere. Again, this reference cell, it's relative, but so we wouldn't want to be moving things around without remembering to come back and fix this formula. Okay, so that just gets us oriented. After we get our graph, we can look at the information, and then of course we're going to put in some unknown values and see what our calculated concentration would be. So this could be used for 2 reasons. You could be using it just to do an extensive calibration with a wide range of concentrations to calibrate your instrument. Or it could be used to generate your standard curve, which is pretty much what we typically do, where we put in a calibration set of information, our standards, and then we put in our unknowns to calculate the concentration of our samples, right? So there's 2 reasons for calibrating an instrument. One is just to calibrate the instrument. Forget unknowns. You just got to make sure it calibrates right. If it isn't calibrating well, if your outputs from your correlation analysis, your linear regression analysis are not adequate, then you got to fix your calibration, fix your instrument before you run any samples. So that's the whole point of what we're doing here. For instrument validation, we want to make sure our instrument is calibrated. Okay, so I came up with some numbers. I mean, this makes us think of values too, right? What kind of numbers would we need to get things? So I came up with 1, 5, 10, 20, excuse me, 25, 35, and 60. So you can put in some numbers of what you think would be concentrations of controls. If it's blood glucose, what would be the levels you'd want for that? So you're working with your biomarker, you're making things up, and then we come up with instrument readings. And I did some trial and error for a while first before I came up with some numbers. My brain doesn't automatically put numbers together like a mathematician, I guess, to know exactly what the patterns would have to look like in order to fit a linear graph. But here we go. You'll see it'll start graphing as soon as I put this number in. A 2, doing a 6, an 8, a 10, a 30, a 60, and a 120. Now you see all the rest of these dots here, so that means we've got to delete. I'm just going to push delete, but it says you can press the space bar. So once you do that, then it graphs to the full set of numbers that you've got. Now look down over here, we have a value here, so something's wrong over on our sheet 2. Let's go see what that is. So something's wrong with our actual readings. Maybe we need to clean this out too. Hit delete. Yeah, see, that fixed it. So we now have a number there and it graphed our residuals. Okay, so for calibrating some instruments, you might need a wide range. Anyway, they just made the template so it could accommodate small to large, and you just need to understand what this is telling you to do after you've put in your initial numbers. So what's important here is you always store an archive of your original template file, right? And then never adulterate it, and then keep working with your template. So maintenance, quality control over your template is really critical too. You screw up a formula or anything in your template, or you let somebody play with it, anyway, you mess this up anywhere along the way, and it can really get messy. Okay, so what we see is we have a line fit, right? So it's the best fit line. We get our formula, y equals mx plus b, and we have our r squared, which, if you notice, is down here, the coefficient of determination, r squared. If we click on this, you can see their formula. If we double click, it should show us see, I'm not really sure how this person got these formulas. I don't know what the SSR is referring to. When you double click, it should show you where those the source of that information is. Is it over here? No. We don't have anything on sheet 3. So SSR, one minus that. Okay, so we'll have to study that one, won't we? And then this is the square root of that. So templates, you have to have trust, right? Are they accurate? And do you know what you're doing, right? Obviously here, I need to find out what the SSR and the SSY are. Anyway, we're all in the same boat. So now over here you can start putting in some unknowns, if we consider this as a standard curve now, rather than just calibrating our instrument. Sorry, we should interpret this. I'm not really sure of the formula right now, but anyway, once you get your r squared, if it's close, you can convert this to a percent. It's like a 99%. And so if you think of it as a percent, what percent accuracy is your fit to your linear curve? So if it was 75.75, would that be acceptable? It depends upon the instrument, the assay, and all those kind of things. A 0.9345 is pretty darn good. Okay, so you can play with changing numbers up here and your instrument readings and everything, and see how these points deviate from the best fit curve, which, by the way, and I don't know the full formula, but the residuals are representing, see out here at 60, the residual is showing it a little bit above the actual best fit. And then here where it's below, then this one is below. So it's a plus to minus 20 on the residuals. If we kind of treat it like a coefficient of variation, if it's less than a 25%, then that's pretty decent. Now you may want to do a little more investigation on residuals, and right now it's stimulating me to think more about it and want to read more about it, of can I treat residuals just as coefficients of variation? I know they are a parallel of that, but would you treat these numbers exactly the same? As a plus 20 to minus 20 acceptable? Now, since I know that this looks pretty good and my numbers are pretty tight, then that would be okay. Now I may want to go back and reassess, look at my records again. How did I dilute this 20 here? Is there any record? Is there any chance? You might want to rerun it, run duplicates, triplicates, to double check on all your pipetting and measuring and all that stuff. So now what we'll want to do is we put in some unknowns. Any reading, 110, 3.687, Anyway, you can go on and put in just to see how it calculates them. If you click here, you can see the formula. So if count J9 equals 1, so J9, so if something goes into this cell, if it equals 1, if there's nothing in there, that's the binary thing, it's 0. If there's something in there, it equals 1. So then it satisfies this Boolean argument. If so, then you apply this formula. Okay? So these are just ways to see what some of the things you can do with Excel to make it a very flexible and useful and time-saving instrument. Okay, so now what we want to do is generate our report. So in the future, what we'll do is, you see how there's text down here. You can come in and merge a bunch of cells and put in the text if you want. Right. Then you can put text in here if you want to interpret your results or whatever, as we're going to generate a PDF report. I'm not saying that this is the best way to generate a report in an actual laboratory setting, but for our class to submit our assignments, it's appropriate. Okay, so here's what we're going to do. Is I want to do a file, print, and then it gives me a print preview. Okay, so I need to change my port orientation to landscape. Okay, I'd like to get more of this in here, so let's try some custom margins. Go to the 0.25. Good, we've got our critical information in there. We can flip down here to page 2, page 3. So some little thing there, some S somewhere on the right hand side. Over there we might want to go and just tweak that in the spreadsheet to pull it in, but for now I'm not going to worry about it. The reason for doing that is that this is going to be the same as when we do a file save as a PDF. So now we can go back to home and we do a file save as a PDF. And there we are. Okay, so see that S got cut off over there, and that's what threw us into the 3 pages. We got pages 1 to 3. So this includes all of our work. Of course, none of the formula or anything, but you can see how you can end up with text down here. And you see our copyright, and the rights are granted for educational purposes, so we're good. Okay, I hope you find this to be very helpful in getting started with this task.